Section 4.4 is modeling and optimization. So this is a lot of writing. Put down what you need, but we do need some steps or strategies for solving our max-min problems. So let's just write this down and then we'll go through it as we work a problem. First thing to do always is to read the problem and understand it. So understanding the problem, read it all the way through, identify the information that you need. Second, we're going to develop a model for the problem. Sometimes drawing a picture helps, labeling parts that are important, introducing a variable to represent what we're going to maximize or minimize, and then using that variable, this is important, write a function whose extreme value gives the information sought. As we do our first problem, this will make some sense. Sometimes graphing the function helps, knowing the domain. Identify critical points and endpoints. Critical points are where the derivative is 0 or does not exist, and then the endpoints of the domain. Of course, then solving the model would be helpful, and then interpret the solution. What does this mean in terms of the real-world solution that we're looking at? So I hope that you've paused to write that down. So here's an example. A rectangle is going to be inscribed under one arch of a sine curve. What is the largest area? So we're maximizing area that the rectangle can have, and what dimensions will give us that area. So I have two things to answer here. So first of all, let's take a look at our sine function. From 0 to pi would be one arch of the sine curve. So what we're looking for here is a rectangle. It might be there, it might be here, it might be here. We're looking for some rectangle whose area would be the largest area we could get under the sine curve. So we need a couple of things. We need to be able to find some variables that will help us to interpret the area, and then we need to write a mathematical model. So, try and erase this. Oh, there we go. Okay, so this is the rectangle that we're looking for, and we need an area. The area of a rectangle we know is length times height. So I need some expressions to represent a length and a height of any rectangle under the sine curve. So my length is going to be the distance along the x-axis. So for any x, since this is symmetrical, this will be pi minus x. So my distance for the length of any rectangle is going to be pi minus x, taking my x value minus the other x value, or pi minus 2x. My height is going to be my y value. In this case, my height, well, something's going on. My height is sine x. So the area of any given rectangle in terms of x is going to be sine x times pi minus 2x. I want that area to be maximized. Anytime I maximize something, I am going to be doing the derivative. So first of all, my domain for x, should have done this first, is less than pi but greater than 0. So solving for a prime, I'm going to be using my product rule. The derivative of the first times the second plus the first times the derivative of the second. So that's my a prime. I want to set that equal to 0. This is one that we'd be using a calculator for. So we're going to set this equal to 0. Let's write it this way. I'm going to set this equal to 0 and put it into our calculator. And then using our 0 function of our graphing, we're going to be able to find our zeros. So a prime of x, and try this yourself, put this into your calculator as a function under y equals, and find your x-intercept or your zeros of the function. So a prime of x will equal 0 at x equals 0.7104. And there's another one, but it's not within our domain. So for any x value of 0.7104, we will have a maximum area. We should always check to make sure that our critical point is a max versus a min. So if I put this into my function from 0 to pi, 0 to 7.4 for my derivative is positive. To the right is negative, so this is a max. So the x value is going to be 0.7104. If I plug that into my area function, I will get 1.122, and that's my maximum area. And then, of course, I could plug it back into my length and width function to find the dimensions. Okay, so that's a simple max-min problem, maximizing the area of a rectangle. So if you have questions, write them in the margin, and we'll talk about this in class. All right, the next thing we're going to look at is marginal values. So when we're dealing with revenue, maximum profit, things like that, we want to look at marginal values. R of x is our revenue, C of x is the cost of producing those items, and the profit is always revenue minus cost. Marginal revenue, marginal cost, and marginal profit are the derivatives. Oops, that should have been dp. So when they talk about marginal cost or marginal revenue, that is the derivative of our revenue or our cost. So again, write this down, and let's look at a maximum profit example. The maximum profit, if any, occurs at a production level at which the marginal revenue, the slope of the revenue, equals the marginal cost. And I hope that you can see from this picture, if the red line is my revenue and the blue line is my cost, when the slopes are the same, I will have the maximum distance of revenue minus cost. If the slopes are different, they will be approaching each other and getting smaller and smaller and smaller. So my maximum profit is the derivative of cost equal to the derivative of revenue. So let's do one. Suppose that our revenue is 9x and our cost of production is x cubed minus 6x squared plus 15x, where x represents thousands of units. We're looking for a production level that maximizes profit. So again, maximum profit is going to equal our marginal revenue is going to equal the place where our revenue equals our cost. So our marginal revenue equals our marginal cost. That's what we're looking for. So let's find R prime of x. That equals 9 using my function. C prime of x is going to be 3x squared minus 12x plus 15. If I set these equal to each other, I will get a quadratic function. And I'm going to go ahead and try and factor this to find my zeros. I'm going to factor out. Okay, this does not factor, but I can use complete the square. So I'm going to say 0 equals x squared minus 4x plus 2. I'm going to subtract the 2 so that I can complete my square by adding something to both sides. Half of the middle squared is 4. So x minus 2 squared equals, whoops, where's my eraser? Equals 2. Taking the square root of both sides and adding 2. So x is going to be 2 plus or minus root 2. Since I am looking for a profit, that's always going to be something in the first quadrant, so I'm just going to use the positive one. So when x equals 2 plus root 2, I'm going to have either a max or a min. Again, testing my signs, I find that this is the point at which I have maximum profit. So when I have 2 plus root 2, and I can put that into decimal form, I will have a maximum profit for this function. Okay, let's look at one more example. Maximum average cost is smallest at a level where average cost equals marginal cost. Another one that you might be asked to do, we're not going to do an example of that right now, but put that into your notes. We'll look at one later. Let's do this one. Design a 1-liter can shaped like a right circular cylinder. What dimensions will use the least material? So let's draw a picture, and I'm constructing this can, and I want to know, how do I use the least material? Well, the material to make a can is going to be our surface area. The surface area of the cylinder is the top plus the bottom, and those are circles. So I need 2 pi r squared pieces. The outside of a cylinder is a rectangle that has been rolled up, whose length is the circumference, 2 pi r, and whose height is the height. So I need to add the sides of my surface area, 2 pi r h. So that's the surface area of my cylinder, and I want to use the least material that I can. My problem is that I have two variables here, radius and height, and I really want to get this down to one variable. So I need to use the fact that this is a 1-liter can. So a 1-liter can is 1,000 cubic centimeters. And I want that to be the volume of my can. So the volume of a cylinder is pi r squared times h. And I know that that's going to always equal 1,000. So I could solve for h here and know that it's 1,000 over pi r squared. So let's rewrite our surface area formula using just r. 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Cleaning that up a little bit. 2 pi r squared plus, my pi's will cancel and one of my r's will cancel, 2,000 over r. All right, so again, to maximize, I need to find the derivative of my function and set it equal to 0. So surface area prime is going to be 4 pi r, that's it, 4 pi r minus 2,000 over r squared. And I want to set that equal to 0. So let's try this with out using a calculator and see what we can do. Okay. I'm going to multiply both sides by r squared. So I will have 0 equals, just try to make it easier to solve, 4 pi r cubed minus 2,000. Come up here. So now I've got 2,000 equals 4 pi r cubed. Using division by 4, 500, oops, pi r cubed. And dividing by pi r cubed. So r equals the cube root of 500 over pi. Sticking that in my calculator, that's going to be approximately 5.42. So when the radius of my can is 5.42, I can plug that back in to find the height using my original formula, or excuse me, using my volume formula. I can get my height, and then I will have the dimensions for the least material. All right, I know this was a lot, but we will talk about it in class. Put down your notes, and I will see you on Thursday.